Hi everyone, and thanks for coming for our presentation. At the glance, the title of the presentation may be a little bit confusing, but actually what we'll be speaking about today is to doing a distributed malware analysis. There are 4 researchers, so this is a research project of 4 researchers from Intel and ESET, and their names are on this slide are presented in the alphabetical order, and that's about it. Everyone did the same contribution, and all their decisions on this presentation were divided and they're agreed among us. So let's start. First of all, we would like to say that all our jokes or mistakes and other things are no responsibility. And of course, we want to praise our employers for giving us time to work on this research. But in case of any mistakes, please blame us, but not our employers. So before starting this presentation, let's take a look back how originally this research started before. So the guys are already presented in Black Hat 2012 on the distributed environment for doing malware analysis. Actually, they started this project in 2010, and before it was more like ad hoc approach, so you can see all the hardware on the slides. So this time we're made up for this, and our hardware looks like more powerful and more well-structured. But actually, in the middle of the Black Hat rush, some things started to mess up, and Wilmester have put Rodriguez's house on fire. So I hope his insurance company won't see this presentation. Okay, let's start with the agenda of the presentation, and the first thing we'll speak about is actually what motivated us for giving this presentation, our objectives and methodology we're using, what kind of tools, what kind of algorithms. We also speak about limitations of our approach, about some design decisions we put in place in order to obtain results. We'll share with you all the results we were able to obtain in the course of this research, and we'll discuss how those additional information will be shared in the community among researchers. So first of all, I think it's needless to say that year by year the number of samples or a number of malware is growing at an absurd pace. And in the public research, there is a lack of their quantitative analysis of their malware analysis. I mean, we often see words most and many, but actually what's interesting to bring to is actually the numbers and the results of this in-depth research and share it among the community so other researchers can take a look at these results, do their personal analysis, inferences, and this is something that was the driving motto for this project. The main objectives of this project is that to demonstrate that it is possible to do in-depth malware analysis, which is scalable. So we picked up IDPro tool, which is a versatile disassembler widely used in the community, and tried to scale this this tool in the distributed environment to be able to process many samples. Like many samples means in our research we're processing 2 million of malware samples. And of course we will share all the results with the community. It comes to the IDBs or to our tools, scripts, plugins we developed in this course of this research, and any additional information. Some important notes about the methodology. We concentrated our attention on their 32-bit and 64-bit binaries. we didn't impose any limitations on the size of the malware. So we analyzed samples as big as 50 megs and as less as there's only fewer kilos. We explicitly put our preference to the malware written in Visual or C++ because of the algorithms we were using for this research, because they were mostly working with this platform. So that's why we were targeting only Microsoft Visual C++ binaries. Information about the distributed environment actually was presented at BackHat 2012, so we're not going to speak about this at this presentation. And if you're interested, you can get back to their material and learn how it looked like. This is a brief overview of the process. So we have several phases. Let's say we have 4 phases here. At the first phase, we were collecting samples. What it means collecting samples? We had samples from multiple public sources, and the idea was to obtain 2 million of samples which meet our requirements. It means that they're Microsoft Visual C++, 32-bit or 64-bit. So we had to process the way more. We were processing about 15 million of samples, and after filtering out all the rest, we finally obtained our collection to work with. After this, we pipelined the samples and this connection in the distributed environment, and we started the process of the information extraction. So actually, we were running IDAPRO with all the plugins, with all the scripts which were generating output data. And then go there 2 phases, combining, aggregating all the results, and generating statistics and charts, which we'll present at this presentation. Another important thing here is to say that we were considering only static analysis. Why did we consider only static analysis? Because, well, generally, it is faster than dynamic. We don't have to take care of setting up execution environment for the binaries. And in our case, this was one of the key design criteria, because we had a lot of samples and we were limited in the computational power. Yes, we know that static analysis is prone to anti-disassembly tricks. It has some limitations. It can be exploited by the malware. But on the other hand, IDAPRO was proven a nice tool to do this analysis, and there is a lot of scripts and plugins available in the community to do here. So let's talk about how we were doing this, or what kind of algorithms and tools we were using. So we were using primarily the intermediate representation in the IDAPRO decompiler, which will refer to C3. So basically, C3 is the intermediate representation of a decompiled function in the IDAPRO decompiler. And we were dumping C3s for some IDAPRO recognized functions. We didn't dump for every function. We'll explain later why. We were reconstructing Microsoft Visual C++ types from the binaries and doing cross-correlation between them. We also performed a depth analysis on their C3s we dumped, because it was really interesting to know, okay, once we obtain a C3 from the binary, it's interesting to know how deep it is in their call graph. Like, what is the distance from the entry point to this C3, because this information is really useful for malware analysis, how deep you need to dig in to reach some interesting function, or in case if you were developing an emulator, how deep do you need to emulate your application to be able to reach some interesting functionality. We were also detecting and marking crypto routines, which we were using AS hardware instructions and GetSec detection. This is really interesting. For instance, GetSec to understand how many malware it is actually using this instruction to detect a virtual execution environment and to evade it. Another topic which we're covering here is their using this pointer in their object-oriented languages. because there are some compilers, and even within one compiler, due to different optimization tricks, this pointer may be used using different registers, E6, ECI, EDI, and that would be interesting to know, okay, how this pointer is used. And actually, this helped us to filter out Microsoft Visual C++ samples out of all the collection we were working with. And in the next slides, I will present some limitations and designer criteria which we were using for Hexarrays Code Explorer for dumping C trees and C++ types, for doing depth analysis and detecting crypto stuff. So let's first start with the C tree analysis. So the process is rather simple. We were enumerating routines recognized by the IDA in the IDBR. We were obtaining intermediate representation and doing C-tree normalization. So basically, we limited the number of C-tree process here. Like we processed first 60 routines of size larger than 1/16 hexadecimal, up to 30 crypto routines, and 30 other functions bigger than 60 bytes. So some important note here about justification of these numbers. There is no real scientific proof for choosing these constants, magic numbers. These numbers were chosen empirically when we were experimenting in our research, doing it on their smaller sample set, and here, like, how does this feature? Because if we put your numbers bigger, we can get more results, which will be a little bit more noisier. If less, then there's going to be not enough data. So empirically, we came up with these constants, and all their results actually presented in this research will depend on these numbers. So we were obtaining this number of C-trees, and we were doing C-tree normalization. So normalization is done to do a comparison of the C-trees. You can see a reference to the implementation of this function in the source code of the plugin, Hexarrays Code Explorer, which will be put after the presentation. So all the details about normalization, because normalization is actually removing all the information which can introduce the noise in the C-trees in the intermediate representation, and basically only consider the structure of this C-tree, and we can do cross-correlation to see if the functions are different in some way, but generally their control flow is the same. We will end up getting the same normalized C-trees. Another approach which we did is dumping C++ types. So we were scanning for virtual tables in the binaries. Since we were targeting Microsoft Visual C++ compiler toolset, we were looking for those virtual tables in the sections RData and data. And if we didn't find anything in those sections, we were going to the data section to look up for virtual tables. Sometimes their malware renames the section. So in case we didn't find any air data or data section, we were looking at other data sections. After identifying virtual tables, we were reconstructing types, actually, which we were using them. By means of reconstructing type, I mean a C-structure representation of this object-oriented type. We were scanning through the IDBR for possible types, identifying their constructors, and using these constructors, we were reconstructing their C layout. During this research, we decided to only dump types which has at least 4 members. If we have fewer than 4 members, then we were rejecting this type. The justification is for this because during our analysis, we've seen a lot of types which has only 1 member attribute or 2, and there is a lot of them throughout all the collections, so these data are useless when it comes to finding similarities. We were doing also a C-tree depth analysis to find, okay, we have a C-tree, how deep it is from the entry point. So we were enumerating cross-references recursively until we reach the entry point, or we reach a limit of we were reaching a limit of 100 nodes there. And we were using a breadth-first search graph traversal algorithm. And then once we obtained these, we were dumping some statistics like distance from the entry point, depth counter, and number of the cross-references. When it comes to finding the crypto instructions and getsec, we were using the following approach. So we were analyzing executable sections and a section with the entry point in case your entry points to their non-executable sections. So this happened as well. And we were limiting the number of the process size of the section, so we were scanning only the first half of the kilobit of the section, and we were doing a linear sweep disassembly, which was very fast. And we were just rejecting some candidates if there is there are some bad or non-recognized opcodes in their linear sweep disassembly. And regarding the this pointer usage in the samples. So we use this approach to first filter out the samples which are not relevant, which are not Visual C++. So the idea was to check up to first call instructions from the entry point, and then we were scanning 5 preceding instructions for any manipulation with the E6. Not any manipulation, but actually instructions which are load in value. So this is either move instruction or load effective address instruction. And then we were computing a percentage of calls with load in E6. Later, as Gabriel will show, we defined some threshold constant when a percentage of these calls with manipulating E6 is higher than this cutoff or constant. This sample is considered as my Visual C++. So now a few words about distributing IDPro. IDPro is frequently blamed as a very slow, very huge disassembler. Well, that's because first it was designed for interactive analysis. There is an interaction between the user and the disassembler. But when we tried to scale this or to do run in the batch mode, we were really surprised with the performance of this tool. Probably because of the structured data format that we're using, because you're like looking up some functions or C trees or whatever was really, really fast. But at the same time, there is some disadvantages. The SDK was really complex and poorly documented, so in most of the cases was trying to playing with the routine and figuring out what this parameter is about, and so it was a little bit challenging. And we were able to achieve a good performance in the commodity hardware. On the other hand, some plugins that we were using are not cross-platform because there were some portability issues. And at the same time, the other plugins are usually not made to scale because they were designed with the goal to the interactive analysis. And they were targeting a single sample analysis while we were running them in the batch mode. So I think this is this basically concludes the first part of the presentation about our motivation, about our methodology, constraints, and algorithms. And now I'm passing the word to Gabriel, who will explain who will present you actually the data and statistics we obtained in this research.
Okay, guys, so as Jinwon mentioned, right, all that constraints and all that limitations, they have a direct influence on the numbers. The idea now is you guys will see the statistics here and you know what it means, the number. So first we start here. We pre-processed around 80 million malware samples, unique malware samples. We did some basic analysis on how much of them are packed and how much of them are not packed. The numbers were 69% not packed. This number is pretty consistent and pretty compatible with all the research we presented in the past and the numbers we can find of other researchers. But since for this research we have the restriction to prioritize Microsoft Visual C++ samples due to the type reconstruction algorithms, we tried from the not packed samples, just analyze the not packed samples, right? Otherwise it would be analyzing the same code many times. From the not packed samples, just 13% are actual Visual C++. This number is interesting because last year we did the same statistics, but for the whole set of malware, include both packed and not packed. And this number was around 40%, between 50% of all the samples using Microsoft Visual C++. So once you get the not packed samples, these numbers reduce a lot. So this is very interesting. So this is not that prevalent, and some numbers might show. So, we used the ASNI optimization, the instructions to optimize the ASNI, right? And we had a question, so how is malware is taking advantage of that? Like for the encryption? So we asked the question, and among all the samples analyzed, just 18 samples actually using the ASNI instructions. So there are two charts here because of the comparison. We want to know, we developed a very fast and simple approach using linear sweep, as Eugene mentioned, to detect the same instructions. We were expecting to see a lot of false positives in this approach. And indeed, it was the opposite. We got a lot of false negatives, right? IDA Pro was more effective in detecting this, and the time constraint was not actually, it did not increase a lot the complexities. Another question we have, it started on the presentation we did this year in Troopers. We started thinking, getsec instruction is the TXT instruction. It actually, if it's inside a virtual machine, it may be dependent on the hypervisor behavior. So that can someone use getsec to fingerprint hypervisor or to detect if you are running inside a virtual machine? And if this case, if this is possible, are malware using this? So we analyzed the getsec instruction with the linear sweep approach, and we found that 4% of all the samples used getsec. This looks huge, so probably there are some false positives here, even though we analyzed a couple of the samples and it's indeed we're using getsec. I think this is an interesting number. Regarding the objective orientation heuristics, the one looking for the load ZCX before calls, we got the prevalence here. So the more prevalent was 4 and then 18. So 4, the number important here is the 30. So what did it mean? All the malware with 30% of the calls loaded in ZCX were actually Visual C++ samples. So this does not mean that all the Visual C++ samples have this characteristic. But all of the samples with these characteristics in our research show that it was Visual C++. So this number is interesting. All of them will be available for the researchers later. This may or may not be a good indication to detect packers, compilers, and the specific behaviors of malware. Okay. So now regarding C-trees, we limited the analysis to 8.5 more or less million C-trees. This is what we analyzed much more. All the results we're going to share, we have all of the information, but for this part, just consider the first 8.5 because this is a huge number. So there is something interesting here. Here is the top 10 repeated C-trees. So C-trees with 40,000 repetitions is around 0.48% and so on. What is interesting here is if you see the total. If you get just the top 10 C-trees that got some repetition, this means that 2.76% of all the C-trees are actually covered. So this shows that this kind of analysis is really good to assist malware analysts on which C-trees to focus. Because now if you just focus on the top 10 repeated C-trees, you are covering 2.76% of all the C-trees. So this shows that it's really assisting the analysts. Of course, the analyst needs to go analyze, but if you find a characteristics of them, all of the other is actually covered. So now another number here. The percentage of the unique C3s that got repeated. So we got all the 8 million C3s we extracted that are normalized, as Eugene mentioned. So in the normalization, we extracted the specific characteristics. So now we are analyzing the behavior, not the specific constant. So if someone is doing 1 plus 2 or 2 plus 1, the normalization remove this dependence. We are just going to do the correct operation. So we noticed that 30% of the unique C3s got at least 1 repetition. And the big majority had no repetitions, right? Again, these numbers is completely tied with the methodology and the thresholds we established, and we should be presented in the previous section. Now, that other chart was regarding the C3s. Now, let's get the malware having that C3s. So we found that we had, among all of the malwares, 9% have some similarities. I mean, 9% of all the malwares have at least 1 C3 repeating among all the sets we presented. So this number depends on the scenario you are looking for or the characteristics you are planning to look for. Tuning the values will give a better result for your specific scenarios. Okay, so now what we did? We got many C3s, right? Let's see how much of these C3s is reaching the entry point. I mean, if there is a path between the entry point and these specific C3s. This is what this chart is showing. So we noticed that of all the C3s, 44% we found a path to the entry point. So now it comes a question, right? What is the depth we go? This number is interesting to show us when you're doing the analysis of a malware to prioritize where our C3s of interest is located, right? So using the heuristics, we saw that the average depth of the C3s that reached the entry point was 5.2 more or less, 5.1940 nodes. So it means that they are 5 calls with a standard deviation of 2.35 from the entry point. And also, we got some other result here. Is how much percent of these C3s is actually direct from the entry point. Like the entry point is directly calling the C3s. Then the result is actually around 1% of all the C3s. This number, we can definitely see it as a noise in the research because probably the entry point, the function calling direct, it should be a helper function or an initialization function, constructor stuff. So yeah, this is what this number. And then the max parents. So now we got C3s, right? How many parents does C3 have? It means how many other functions are calling this specific function, right? And we got the top 10 here. As you see, the number of parents here is huge, like 11,000 or something. But you see that as the top 10 goes down, the number significantly goes down, right? Yeah, and this is what the chart is about. We have many other data. We have actually a huge amount of information. We can get all the information is structured in databases. We can just query. We just got for you here guys, the ones we thought are more interesting. But yeah, all of the data will be available, and any researcher can actually query the database and do whatever you guys want with the data, right? If you think there is another statistics, okay, go on. Have the data, you can just go and query. Okay, so now I'm going to pass the word to Alex Matrosov. He's going to talk about validating this methodology in malware.
So in this part, we will be speaking about analysis some targeted C++ malware, and we choose a couple of families for this analysis. But the most interesting set, it was Animal Farm. It's mean Babardino and Barney Kasper. It's 4 samples, and between these samples, it's a lot of interesting similarities here. So, and a lot of, not a lot, but a couple of researchers already analyzed deeply this family, but we found something interesting which not presented before on the others conference. So here's some references on the researchers, and Casper, Barney, Babar, and Dino, it's developed on Visual C++ and used some object-oriented interfaces and technologies, and we found interesting similarities between different virtual tables, but looking on these screenshots, its screenshots showed dumped virtual tables by Hex Race Code Explorer plugin, and here we try to show how our approach working on the small sets of the samples and mixed with some kind of manual analysis. All names of these virtual tables was reconstructed by manual analysis, and looking on the Casper, here is the one big offset virtual tables, but it's separated on the Dino. So, okay. And Casper and Dino have some interesting interface, run key, for installing the malware into the system. We reconstruct the interface, and it's looking by this chart and has 4 objects. And here is the Casper and Dino auto-deletion mechanism. It's deleted by command from CNC and has just 3 methods. So we have some restrictions in our approach and methodology. We don't compare virtual tables which has less than 4 virtual methods. And looking here. Here is some comparison exactly how object creation and how constructors looked. So if you're looking on the run key in Casper, it's created 2 different objects. And Dino creates the same interface by 1 object, but bigger. So if we looking on the reconstructed types by Code Explorer plugin, it's looked not similar, and it's exactly confirm our methodology and shows some limitation by our manual analysis. Okay, and let's try to find some similarities between others. Dino face NBOT. We going in the same way. We use it for this part of research, the same tools and totally same methodology. And looking here, it's had some similarities between virtual tables in the different malware. Okay. And also, all the names reconstructed here, it's reconstructed automatically by new functionality of Hex Race Code Explorer plugin, which working with some RTTI reconstruction metadata. We implement new algorithms here, and it will be released new version after Black Hat. So, and looking deeply into the constructors of the object for Dino and NBOT, it's this object it's communicating with command center and gets the command and provide some information to command center from the infected machine. Here are the reconstructed types from Hex Race Code Explorer. And we can see these types looks really similar. And our algorithm detects this similarity. And it looks like our approach is working. And it's really good example how we can find the similar, totally similar created object and reconstructed by Code Explorer plugin. And it's detect similarities into the code. So definitely discuss this kind of similarities. We not discuss nothing. We just discuss similarities between code, and it's not point for new some. It's sometimes point to new attribution, and in this case, yes, here is a connection between. All similarities which recognized it and found in these 5 malwares, and it's the connection between these malwares. If you look in here, you can find a lot of similarities between different interfaces, and we already show how it's looked on virtual tables dumped by Hex Race Code Explorer. So, and other final results of this analysis, it looks like we have summarized the previous slide. It shows how many similarities we found between each other of this set of the malware. And in our opinion, it's a pretty much interesting method to find some connections between different malware families and found the new way to some attribution between operations or something like that. So, and currently we're going to conclusion of our talk, and we have some interesting information after conclusion. So, and Eugene, conclude our talk.
Yes, so basically we made it almost to the end of this presentation. So just to recap what we were speaking today about. So we basically started doing a distributed large-scale in-depth malware analysis using IDA-Pro, which was like personally from our experience, it was very challenging because the IDA-Pro was designed in mind for interactive analysis of interacting with the researcher, and we tried to put it in completely batch mode without any dialogues and without any interconnection, running plugins and scripts in the same environment. So, surprisingly, it worked well because we were thinking we will have the way more problems with this, and the performance we obtained was really interesting because I'm not sure if I mentioned here, we had in our research 10 machines with 8 cores per machine. And we were able to run 50 IDA-Pro instances per machine. So in total, we were running in parallel 500 IDA-Pro instances. So that was quite impressive. And we would like also to bring attention of the IDA-Pro plugin developers to like a call to action to add a batch processing to their plugins to facilitate their integrations, their integration to this distributed analysis. And on the other hand, if you want to run your plugin on the large data set, on the large set of samples, please let us know, because that would be an interesting experience. You can like fuzz and stress test your plugin, because even now with our plugins, we were discovering the way a lot of implementation bugs which really helped improve the quality of the code. And of course, we will share results of this testing with the community, because this research is public and all the results will be shared. So all the resources of the presentations of this presentation, what comes to slides, code, data, IDBs will be made available. So please stay tuned at this link. Well, we have a lot of data. I think we have about several terabytes of the IDBs. So we are still figuring out the logistics, how to provide this data to you. So if you have any suggestions, please feel free to drop us a line and to help us. So that would be very, very much appreciated. And this research, we are significantly improved the X-Ray Code Explorer plugin, and we will be releasing a Black Hat edition with a lot of improvements. One of the main things is that finally this is cross-platform, so you can compile it both for Windows, Linux. But it's important to know that this plugin will be targeting only Microsoft Visual C++ or binaries, because this is the algorithm we are using. And it's able to run in the IDA batch mode, which we're using in this research, so you can basically get this compile and reproduce this research or play with this data. A few acknowledgements here. We would like to explicitly say thank you to Ilfat Gulfanov, X-Ray team and the community of your plugin developers and script developers around this, because without their support, this research could have not existed. And in the shameless marketing way, I would like to announce that a book on the rootkits and bootkits is available now in early access. So this is a book co-authored by me, Alex Matrosov, and another famous researcher, Sergey Brados. So in this book, we summarized all our experience, which we accumulated over the years while working in the security industry and doing reversing of the bootkits and rootkits. So this book is available at this URL. It's in early access. We're still working on it, and we would really appreciate any feedback on this book, what you would like to see or what you would like to add, because there are some chapters available, there is a table of contents, and we're really looking forward to the feedback. And that's about it. Thank you for your attention. I think we have enough time to take some questions.
Can you do this?
Oh, thanks. Thanks for a great talk. I wonder if you can give some information about the time required to process 8 million samples and what kind of architecture you had. If you did present, I might have missed the first part of your talk, so if you could say it again.
Okay, so the question was to speak about how much time did the processing take, about the architecture of this distributed environment. I think this question may be handled by Gabriel or Rodrigo.
Yeah. Hello? It's over. This whole analysis took for us around 1.5 days with full power, 10 machines.
10 machines?
10 machines.
And what kind of core memory, could you have any idea?
Each machine has around 16 gigs of memory and 8 cores per each. Okay. Now the core may be Xeon, basically Xeon 2.4 gigs. I think this is 2.4 gigs, I think. Most.
And how long did it take to process all the samples?
Yeah, 1.5 days.
How many?
1.5 days, like 1 day and a half.
1.5 day?
Yeah, 1.5 day process, yeah.
How much is the storage it creates? How much disk space you need to store all the...
The total storage of the results, I don't have the information.
Roughly,
but,
okay.
Around 2 teras or something.
Okay, all right, thanks.
So on the getsec instruction, you said that you saw 4% of the machines actually using getsec, 4% of the malware using getsec. I missed the part. Were you saying that you looked into it and you confirmed that some definitely were using it as like a signature to anti-VM signature or something? Or did you say you just hadn't looked into that further?
Yeah, actually, we looked to the getsec instructions on the linear sweep disassembly. Right? An approach that we know that can generate a lot of false positives because the numbers is huge. We're not expecting that much. What we did, we had a test bed before running all the millions of samples. We had a test bed of a couple samples, actually around 100 samples, and we flagged getsec in these samples. So for this sample that flagged, we on IDA Pro, we open to double check if IDA Pro, that uses another type of disassembly, also triggered this, and it actually triggered. It found a function using getsec, and also it found that this function is calling by another. It was recognized as a function by IDA Pro. So,
okay, yeah, so basically you confirmed it on 100 samples? Or?
We confirmed just in one or two. So sure. We think that this data has a lot of false positives, right? And we don't know if this is actually techniques to anti-VM or to fingerprint or not, because we did not actually go to one sample and deeply analyze to understand the flow. We just look at more the analysis if it's actually indeed using getsec or not. This was a double check we did.
Okay.
But not for all of them, just for a couple.
Early on, you stated that you only analyze unpacked portable executables. So initially, was there an automated means to compare the size on disk to the virtual size, or did you use IDAPRO somehow to determine
to detect whether it's detected or not?
Yes.
Yeah, we use a set of IARA rules for that.
Okay.
Okay, guys. So I think if no more questions, that's it. So thank you very much for your attention, and yeah, keep posted. We're gonna share all the results with everybody. Thank you very much.